Hello, in today's video, we are looking at the rational zeros theorem. Our goal is to answer the question, how do you find all the possible rational zeros of a function? And essentially to do that, we're going to learn how to apply the rational zeros theorem. Now that theorem is stated below, we're going to talk through it quick and then look at some steps to actually answer this question and then look at a couple of examples. The rational zeros theorem says, let f be a polynomial function of degree 1 or higher of the form, which is listed below, where each coefficient is an integer. Now that's super important for us, so we need each coefficient to be an integer. Remember, your coefficients are your numbers in front of x. In our case, they're a sub n minus 1, a sub 1, and this one here, a sub 0 on the end. Now, in order for them to be integers, that essentially tells me that they each need to be whole numbers. So if any of those highlighted parts of my function are decimals or fractions, we can't apply this theorem. We need them to be nice whole numbers or integers in order for us to be able to move on and actually apply our theorem. Once we've checked that, we are good to go. Our theorem goes on to state, if p divided by q in lowest terms is a rational zero of f, then p must be a factor of a sub 0, and q must be a factor of, sorry, there's a typo, a sub n. So this is telling me if I take my factors of my constant term, a sub 0, and I divide them by my factors of my constant term, a sub n, then it will give us a list of all the possible rational zeros of our function. Again, for something to be rational, it has to be a whole number divided by another whole number. So we're going to be looking at some either fractions or some things that work out to be nice whole numbers after we divide them. We're going to go ahead and look at some steps to solve this problem and answer this question, and then do a couple of examples on the next few slides. Here is a list of the steps we can use to find the potential rational zeros. The first one, you have to determine if your function has integer coefficients. Again, that means that each number in front of our x is a nice, pretty whole number. If it's a decimal, if it's a fraction, we can't use this theorem. So if we answer yes to this question, we're going to move on and do the rest of the steps. Whereas if my answer to this question is no, we have a fraction or we have a decimal, then I need to stop and I can't use my theorem. So if I say no to that question, I can't solve the problem in the way that we're going to for the rest of these. But if I do say yes, we'll move on to step 2, which is to list all the integers p that are factors of the constant term. Then we list all the integers q that are factors of the leading coefficient. And last but not least, we form all the possible ratios. Again, we're looking for rational zeros, so they can be fractions or they could be whole numbers. For example 1, if possible, list the potential rational zeros of f of x equals 2x cubed plus 11x squared minus 7x minus 6. So we're going to start by looking at our coefficients. We have 2. Oh, sorry, I wanted to highlight her. Let's try that again. We have 2. We have 11, we have negative 7, we have negative 6. Those are all integers, so that means we can use our rational zeros theorem. So since those are all whole numbers, we can move on to the next step. Step 2 is to list all of the integers p that are factors of the constant term. Our constant term is negative 6, so we have a naught equals negative 6. And then we have to list our factors. Essentially, for our p value, we are looking for factors of 6, so things I can multiply to get 6. I know that I can do 1 times 6. I know that I can do 2 times 3. I'm not too worried about the positive or negative here. Essentially, all of our factors to get to 6 for our options for p can be either positive or negative. So when I actually write out my p-values, I'm going to say it could be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. If it's helpful for you to list over here and look at, okay, what can I multiply to get to 6? I know I can do 1 times 6, 2 times 3. I always know I found all the factors when there's no more integers that fit in between my last two. That always helps me. All right, so we finished step 2. Step 3 is to look at our leading coefficient, which in our case is 2. And we want to list all those factors. This one is nice and easy. We have an equals 2. And really we only have 2 factors. We're going to have plus or minus 1 and plus or minus 2. Again, I know that 2 is the same as 1 times 2. Those are the only 2 factors of our thing. The last step is to list all the possible ratios P divided by Q. So we listed all of our P's to start. We need to divide each of them by our Q values. So for the first one, we have plus or minus 1, and we're just going to divide by 1. So divided by plus or minus 1. Then we're going to do plus or minus 2, and still divided by 1. And we're just going to go through all the list of our P values and divide them by our first Q value. Then we're going to do the same thing, only now we're going to divide by our second Q value. So we're doing plus or minus 1 divided by plus or minus 2, plus or minus 2 divided by plus or minus 2, plus or minus 3 divided by plus or minus 2, and then plus or minus 6 divided by plus or minus 2. Now all of those plus or minuses that I double wrote, they're kind of redundant. Each of our terms is just going to have 1 plus or minus, and then we can simplify our fraction. So for my first one, we had 1 divided by 1, which is just 1. The second one, we're going to have plus or minus 2 divided by 1, which is 2. Then we have plus or minus 3 divided by 1, which is 3. Plus or minus 6 divided by 1, which is 6. Then we have plus or minus 1/2. Now I can't simplify that fraction any further, so I'm just going to leave it as that. Then we have plus or minus 2 divided by 2, which is 1. We have plus or minus 3 divided by 2, which again we'll leave. And then my last one, plus or minus 6 divided by 2, which gives me 3. Now if I look at my list here, we do need to double check and make sure nothing's listed twice. We really just need each of our zeros to show up once. So I noticed that we had plus or minus 1 here and here, so I'm just going to go ahead and cross out that second one. Did I want to use an actual pen for that? Yep, I did. I also noticed that we had plus or minus 3 here and a plus or minus 3 there. So again, that one is sort of a duplicate. We can cross that one off. So that means that in total, my potential zeros are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 1/2, and then plus or minus 3/2. Again, those are all of my potential rational zeros of f of x. All right, for example 2, we still have our steps listed above so we can refer to them. But we are going to determine, if possible, the list of potential rational zeros of f of x equals x to the 4th plus 3.2x squared minus 16.83x minus 5.31. Again, the first question that we have to answer is whether or not f of x has integer coefficients. For this one, notice there's not a number in front of x to the 4th, but there is a sneaky little 1 written there. That is not, that's invisible for now, but it is there. And then we have 1, 3.2, negative 16.83, and negative 5.31 for our coefficients. Again, in order to be able to use our rational zeros theorem, we have to have coefficients that are integers. All of these, except for one, are decimals. So these 3 here, they're not integers. Again, that's a problem for us because we can't use our rational zeros theorem if those are not integers. So we're going to write that this one is not possible. Because f of x contains coefficients that are not integers. Again, at that point, I stop. I can't use my rational zeros theorem, so we're done for this problem. That is all I have for you on how to use our rational zeros theorem. Thank you for watching. As always, if you have any questions, don't hesitate to reach out.